This is the beginning of section 4.3, which is titled Weibull distribution. The Weibull distribution comes up because the assumption that a lifetime has a constant failure rate from the exponential distribution is often too restrictive or inappropriate. Mechanical items oftentimes degrade over time, and hence those fall in the IFR class. So we would like to get a distribution with a hazard function which is strictly increasing in order to model the failure times of those items. The Weibull distribution is a generalization of the exponential, and it includes the exponential with its constant hazard function, but it also has a strictly increasing and strictly decreasing hazard function. Here are the first four of the lifetime distribution representations. The survivor function is e to the minus lambda t to the kappa. Now the problem here is that there are many different ways to parameterize the exponential distribution. Not everybody uses lambda and kappa. Some people use alpha and beta. Furthermore, not everybody includes the lambda t right here inside of the parentheses. Sometimes the lambda factor is outside of the parentheses. So there's a lot of different ways to parameterize it in the literature, and that makes it confusing to keep track of one parameterization versus another. So there's the survivor function. If you differentiate that and negate, you will get the probability density function, which looks like this. The hazard function is the ratio of the probability density function to the survivor function. So that is f of t over s of t, and if you look at those two, you can see the exponential terms dropping out, and you get this. And finally, if you integrate that from 0 to t, you get the cumulative hazard. The fifth lifetime distribution representation we will revisit on the next slide. All of these are, of course, on the support t is greater than or equal to 0. Lambda is a positive scale parameter, and kappa is a positive shape parameter. The hazard function for the Weibull distribution approaches 0 from infinity when kappa is less than 1, and that is the DFR case. It is constant when kappa equals 1, and that is falling in both the IFR and DFR classes. That is the exponential case. And finally, the most common of the three is it increases from 0 for kappa greater than 1, and that's the strictly monotone increasing hazard function, and that is in the IFR class. The reason this one is the most common is most things in the world degrade with time. In other words, they age. Pair of special cases. The Weibull distribution with a shape parameter of 2 is known as the Raleigh distribution. And when you get your kappa somewhere between 3 and 4, it has a bit of a bell shape to it. So if you ever have some data, lifetime data, and you draw a histogram and it looks like it is bell-shaped, the Weibull may be a good fit with a kappa somewhere between 3 and 4. Now the mean residual life function here is quite unpleasant. Here is the formula from the 5 by 5 matrix. When you plug in the survivor function, take its reciprocal, you get that. The survivor function is here, and that is a difficult integral. However, if you make the substitution u is equal to lambda t raised to the kappa power, now what you'll have is this term that's circled right here will reduce to e to the minus u. And now it starts to look a little bit like a gamma function, And unfortunately, the limits don't go from 0 to infinity, so that forces you to invoke the incomplete gamma function. So here is an expression for the mean residual life function. In order to compute this thing, you have to not only have a gamma function, but you also have to have an incomplete gamma function to evaluate that for particular values of t, lambda, and kappa. Here are graphs of the 5 lifetime distribution representations for the Weibull distribution. And this is all done with a scale parameter of 1. So if we look first of all at the probability density function, notice that when kappa is equal to 1, you get the exponential distribution. When kappa is less than 1, you get a probability density function that has a high probability of failure early and then decreases from there. And notice for kappa equals 2, that's the Raleigh distribution from before. And for kappa equals 3, this is that range from 3 to 4. It has kind of a bell shape to it, and that can be valuable in some applications. Then we go to the survivor function. So again, for those same values of kappa, there is your survivor function. And you'll notice they all pass through this point right there. That point is known as the characteristic life, and that is 1 over lambda. It turns out that all Weibull survivor functions will pass through the point 1 over lambda, 1 over e, and that is the point that you're seeing there on the survivor function. Now to the hazard function. Notice for kappa equals 1, you have a constant hazard function. You are in the DFR case when kappa equals 0.5, and you're in the IFR case for kappa equals 2 and kappa equals 3. The choice between those various values of kappa will be indicated by how quickly this particular item is wearing out. Then you go to cumulative hazard function. You can see the same values of kappa here. Notice that all Weibull cumulative hazard functions are going to pass through the point 1 over lambda 1, and that is this point right here. And finally, the last is the mean residual life. And here is the mean residual life in the, let's see, kappa equals 0.5. That's the DFR case. And then kappa equals 1 is the exponential case. And then kappa equals 2 and kappa equals 3 is the increasing failure rate case. Notice as the hazard function increases for kappa equals 2 and kappa equals 3, the mean residual life goes down because the items are wearing out.